White dwarfs, neutron stars, and black holes are the final stages in the evolutionary life cycle of a star. When a star is born, gravity compresses a massive amount of matter together. Under extreme pressure, matter particles will undergo nuclear fusion. It releases energy in the form of radiation, counteracting the collapse due to gravity. This reaction combines light elements such as hydrogen to form heavier elements. However, as the synthesis process moves to heavier elements, the amount of energy released progressively decreases. Eventually, the star exhausts its fuel, and its subsequent fate depends entirely on its initial mass. For a star to evolve into a white dwarf, its initial mass must typically be less than about 8 times the mass of the Sun. After undergoing evolutionary stages, the remaining core of the star, with a maximum mass of approximately 1.4 times that of the Sun. Under the radiant moonlight, the white pebbles suddenly began to glisten, as if they were transforming into shimmering pearls. The collapse of a star is prevented by electron degeneracy pressure, a quantum mechanical effect stemming from the Pauli exclusion principle. This principle forbids electrons from occupying the same energy state, countering gravity's tendency to force them closer together. Due to its relatively small mass, this pressure is still sufficient to maintain the white dwarf's stable structure. Most small and medium-sized stars end their life cycle as white dwarfs. Near the end of the fusion reaction stage, when the hydrogen is depleted and has been completely converted into helium, the star begins to expand, becoming a red giant. It then expels the majority of its material outwards, forming a planetary nebula. The remaining core, with a temperature reaching 100,000 degrees Celsius, will become a white dwarf. A typical white dwarf has a mass comparable to the Sun, but its size is only slightly larger than Earth, making it one of the most beautiful forms of matter, second only to neutron stars, hypothetical quark stars, and black holes. Interestingly, the more massive a star is, the smaller the white dwarf it leaves behind becomes, because gravity compresses its internal matter more tightly. The Chandrasekhar limit is the maximum mass a white dwarf can have. If this limit is exceeded, the electron degeneracy pressure can no longer withstand the gravitational force, leading to a further collapse to form a neutron star. However, most stars avoid this fate by releasing their excess mass into space before completely collapsing. The surface gravity of a white dwarf is 350,000 times stronger than Earth's. A person weighing 68 kilograms on Earth would weigh up to 23.8 million kilograms on the surface of this star. White dwarfs have extremely high temperatures and emit a brilliant white light due to residual heat generated from their initial collapse. Since there are no further nuclear reactions to supply energy, unless it draws matter from a neighboring star, this heat will gradually dissipate through radiation. However, due to its small surface area, the cooling process occurs very slowly. Finally, the white dwarf will transform into a black dwarf, a cold and dark entity that emits only faint radiation in the radio wave spectrum. However, the current universe is not yet old enough to witness the formation of a true primordial black hole. In a small number of cases, a white dwarf can exceed the Chandrasekhar limit if it is in a binary star system and accretes matter from its companion star. When the accumulated mass reaches an unsustainable threshold, it leads to a type Ia supernova explosion, one of the most powerful forms of supernova. If the accreting material absorbs hydrogen, the nuclear reactions can cause smaller-scale explosions, known as white dwarf novae. These explosions occur only in the outer shell, do not destroy the core, and may recur if the flow of material continues to be replenished. For stars with an initial mass greater than this, typically ranging from 8 to 25 times the mass of the Sun, the remaining core after the evolutionary stages will have a mass ranging from 1.4 to 3 times that of the Sun. At this point, the electron degeneracy pressure is no longer sufficient to counteract the immense gravitational force, causing the stellar core to be compressed further until most of the remaining matter consists primarily of neutrons. At this point, neutron degeneracy pressure, a mechanism that is similar but vastly more powerful than electron degeneracy pressure, emerges and prevents a complete collapse. The result is the formation of a neutron star. Throughout a star's life, a balance is maintained between gravitational force, which pulls matter inward toward the core, and the outward pressure from within, generated by the extreme heat and energy of the thermonuclear fusion reactions burning hydrogen into helium in the core. For giant stars, this process occurs over billions of years until their internal hydrogen is depleted. At this point, the force of gravity becomes overwhelming, compressing the core and causing it to heat up significantly. The rising temperature triggers the process of fusing helium into heavier elements, thereby only temporarily postponing the star's collapse. These cycles repeated over millions of years, causing Earth's core to become increasingly dense and hot, while gradually forming a mass of iron at the center. Iron is the hallmark signaling the end of a star's life cycle. Unlike lighter elements, iron cannot be fused into heavier elements without consuming energy, which causes the fusion reaction to cease. When the stellar core accumulates a sufficient amount of iron, it will collapse at an extremely rapid rate in just a matter of seconds. Under immense pressure, electrons and protons combine to form neutrons, simultaneously releasing neutrinos. Electron degeneracy pressure arises, and it is sufficient to temporarily halt the gravitational collapse. Meanwhile, the star's outer shell is blown off in a supernova explosion, one of the most brilliant and violent explosions in the universe. The remaining core, with a diameter of only about 20 kilometers, became a neutron star. This is one of the densest forms of matter known to humanity. Compared to white dwarfs, the density of neutron stars is billions of times greater. To put it into perspective, a teaspoon of matter from a white dwarf would weigh several tons on Earth, while a teaspoon of neutron star material would weigh billions of tons, equivalent to the mass of a large mountain. The surface gravity of a neutron star is incredibly immense, roughly 2 billion times stronger than Earth's. It is so powerful that it can utterly crush anything that comes near it. When a star has an initial mass greater than approximately 25 times that of the Sun, the remnant core left after evolution surpassing the Tolman-Oppenheimer-Volkoff limit typically has a mass ranging from 2.5 to 3 times that of the Sun, depending on the specific conditions. At this point, the neutron degeneracy pressure is no longer capable of counteracting the immense gravitational force, leading to a complete and unstoppable collapse. The star's entire mass is compressed into a point of infinite density, known as a singularity, and from that, a black hole is born. A region of space-time where gravity is so strong that nothing, not even light, can escape from it. The most defining characteristic of a black hole is its event horizon, a boundary surrounding it where the escape velocity exceeds the speed of light. Any form of matter, energy, or information, once it crosses the event horizon, will be pulled inward with no possibility of return. Since light cannot escape, it is impossible to directly observe a black hole using conventional optical methods. However, astronomers can still detect black holes through indirect signs. When matter from space, such as gas from a neighboring star, is pulled in, it accelerates and